Welcome to our session on Audit Evidence Collection Techniques for Artificial Intelligence. Today we are exploring the absolute foundation of any intelligent system, which is data. We will uncover how data is gathered, categorized, prepared, and protected throughout its life cycle. Understanding this process is not just about passing your certification exam. In your daily professional life, you can use these exact concepts to evaluate third-party software vendors. When a vendor tries to sell your company a new intelligent tool, you will know exactly how to interrogate their data pipelines to ensure they are not introducing hidden risks, biases, or compliance violations into your corporate environment. Every artificial intelligence model requires data to learn and function. If an artificial intelligence system is a high-performance engine, data is the specialized fuel it needs to run. Without this initial input, the system simply cannot operate. When an organization decides to build an intelligent tool, the business case must clearly define where this data will come from, its specific type, its original source, its overall value, and how it will be continuously collected and maintained. During the development lifecycle, we generally divide our data into three specific sets, which are training, validation, and testing. Let us start with training data. Simply put, this is the foundational information used to teach the model. It is how the software discovers patterns, builds relationships, and learns to make predictions. We can approach this teaching process in a couple of ways. The first is supervised learning. Imagine you are teaching a child to identify different types of fruit using flashcards. You show them a picture, and you explicitly tell them it is an apple or an orange. In supervised learning, the model is given input data that has clearly defined, known output labels. The second approach is unsupervised learning. In this scenario, there are no labels. It is like giving a child a massive box of mixed building blocks and asking them to organize them however they see fit based on color or shape. The model must analyze the raw inputs and independently discover the hidden relationships and patterns without any external guidance. Training data can take many forms, from text and images to audio recordings. It can be highly structured, completely unstructured, or somewhere in between. Regardless of the format, training data must be of the highest possible quality and accurately represent the real-world population the model will eventually interact with. If we fail to provide representative data, we risk a phenomenon called overfitting. Overfitting happens when a model memorizes its training material so perfectly that it cannot handle any new, unseen information. Think of a student who memorizes a practice test word for word, but completely fails the actual exam because the questions are phrased slightly differently. Conversely, underfitting occurs when the model fails to learn the underlying patterns at all, leaving it unable to make accurate predictions even on its training material. As an auditor, you must ask rigorous questions about this phase. What specific data was used to train the model? Is it truly representative of the real world? Was overfitting or underfitting identified and corrected? And crucially, was explicit legal consent required to use this information? And has that consent documentation been retained? Once the system has been trained, it must be evaluated. This brings us to testing and validation data. While some organizations might casually group training and testing together, they serve entirely different purposes and must be kept strictly separate. Testing data is the final exam. It evaluates how well the model functionality and predictions handle comprehensive, real-world scenarios that it has never seen before. Sometimes, organizations use synthetic data for testing. Synthetic data is artificially generated information that mimics real data without containing any actual sensitive details. It is incredibly useful for creating diverse and comprehensive testing environments while perfectly protecting user privacy. To create this artificial data, engineers use advanced techniques to teach models how to generate data that follows strict statistical guidelines. They combine deep learning methods with complex tools like generative adversarial networks, commonly known as GANs, and variational autoencoders, or VAEs. Let us translate that jargon. Think of a generative adversarial network as a game between a master art forger and a highly skilled detective. The forger tries to create fake paintings that look perfectly real, while the detective tries to spot the fakes. As they compete, the forger becomes so good that the artificial paintings become practically identical to real masterpieces. When reviewing this testing area, an auditor must ask two primary questions. Was the test data appropriately separated from the training data? And exactly how was the synthetic data generated? After rigorous testing, the model is deployed into the real world, where it relies on production data to succeed. This is live information gathered from active environments. It might be sourced from a public population, like fitness tracker statistics, or it could be purchased, crowdsourced, or collected internally from systems the organization already owns. The key audit focus here is monitoring for drift. Drift occurs when the real world changes over time, but the model does not adapt. Imagine a system designed to predict traffic patterns based on highway layouts from 10 years ago. Because new roads are built and populations shift, that old model will eventually start giving terribly inaccurate directions. Auditors must verify what data is used in production, exactly how it was sourced, and how it is constantly monitored to ensure the model does not drift off course. Now let us examine how this information is formatted, looking at both unstructured and structured data. Unstructured data lacks a predefined format or schema. It does not fit neatly into a traditional database and usually does not have a data dictionary explaining what it means. This category includes loose text files, office documents, audio recordings, video clips, and images sitting in file shared directories. It also includes external sources like social media posts, websites, and background metadata. Auditors have used unstructured data for years by pulling files from department shared drives. However, using this data for artificial intelligence poses massive risks. Auditors must fiercely verify where this unstructured data lives and the exact access limitations placed on it. Imagine a company deploys a powerful internal virtual assistant to help employees draft emails. If folder permissions are misconfigured, that intelligent assistant might accidentally index a restricted folder containing confidential payroll spreadsheets. Suddenly, any employee asking the assistant a casual question might receive the salaries of the executive team in the response. On the other hand, structured data is highly organized in a predefined format, typically housed in a relational database. It comes with a schema, which is essentially the architectural blueprint of the database. It also usually includes a data dictionary that lists metadata describing the exact type, size, format, and relationships of every single data element. Historically, auditors query this structured data for standard transaction testing. However, a major paradigm shift is occurring. Audit departments are increasingly collecting and hoarding vast amounts of structured historical data in their own databases to perform continuous, automated auditing. By building these massive data stores, the audit department inadvertently becomes a highly attractive target for both internal and external bad actors. Auditors must now strictly adhere to organizational policies, international standards, laws, and regulations to ensure their own data stores are adequately protected. To make any of this raw data usable, we rely on a critical process called extract, transform, and load, widely known as ETL. First, the data is extracted from its original storage repositories. Next, it is transformed. Transformation is the cleaning process where data is standardized and scrubbed so it is perfectly usable for analysis. Finally, the cleaned data is loaded into the target system to be queried and tested against specific criteria. Auditors frequently use software tools like Audit Command Language, Tableau, and Power BI for this workflow. With artificial intelligence, this entire end-to-end process can become fully automated, though that automation relies heavily on complex coding. Furthermore, audit teams are beginning to deploy their own artificial intelligence agents for data collection and fuzzy testing, which involves looking for unexpected patterns or predicting outcomes. Imagine an intelligent agent programmed to monitor a corporate banking portal. The moment a new payee account is added, the agent automatically extracts the banking details, transforms the formatting, and runs logic tests to flag anomalous routing numbers before a human auditor ever logs in. When collecting evidence, AI auditors face serious risks regarding data manipulation. The three main threats are bias, data poisoning, and adversarial attacks. Because humans are inherently biased, programmers and data scientists can consciously or unconsciously introduce prejudice into their models simply through their selection of training data. If a medical diagnosis tool is trained entirely on health records from a single demographic, it will systematically misdiagnose patients from other backgrounds. Auditors must actively hunt for these skewed outcomes while also being highly aware of their own personal biases during data selection and analytics testing. Next is data poisoning. This occurs when a malicious actor intentionally introduces corrupted data into the system to permanently skew the output to their advantage. Think of a saboteur sneaking into a winery and pouring vinegar into the grape vats. Every bottle produced from that batch will be ruined from the inside out. Strong data management controls are essential to help auditors verify if raw data has been maliciously altered. Finally, we have adversarial attacks. Unlike poisoning, this targets a live model by manipulating the input prompt to deceive the artificial intelligence into making incorrect decisions or providing harmful output. Imagine wearing a specially designed pair of glasses with a geometric pattern that completely tricks a facial recognition camera into classifying you as a stop sign. This is especially damaging for large language models. To mitigate this, engineers use specific open source tools to stress test the robustness of the system against deceptive prompts. As internal audit teams build these testing capabilities, they must be hyper aware that their own testing tools might be vulnerable to similar exploits. Our final data collection method is scraping. Scraping involves deploying automated scripts to crawl websites and aggregate vast amounts of public information into a single location. This technique is heavily used to gather the massive volume of data required for large language models. However, because modern websites are highly dynamic and constantly changing, scraping is becoming much less efficient than using formal application programming interfaces or APIs. Using an API is like politely asking a restaurant kitchen for a recipe card and receiving a perfectly typed document. Scraping is like sending someone to peer through the kitchen window with binoculars to manually write down what the chef is doing. Because scraping often pulls in messy or broken code, it frequently requires manual intervention to clean the gathered data. As an auditor, you must ask several critical questions. How is the scraped data validated? How efficient is the process? And do the scraping scripts need frequent tuning? Most importantly, does the manual intervention required to clean the data introduce new integrity and security concerns? Let us summarize our key takeaways. We explored how the foundation of AI relies on carefully separated sets of training, validation, testing, and live production data. We reviewed the critical differences between structured databases and unstructured files, and how extract, transform, and load pipelines make this information usable for analytics. Finally, we navigated the serious risks of bias, data poisoning, adversarial attacks, and scraping vulnerabilities that threaten system integrity. All the important topics and concepts from this session are covered in the multiple choice questions on RooCloud.com. You should ideally solve the chapter-wise questions to reinforce your learning before moving to the next session. Thank you for joining me, and I will see you in the next episode.